morning. Hello, Chris.
Morning. How are you?
I'm good. It's actually a bit chilly today,
It is, yeah.
but I think it's going to warm up, isn't it? We're going through that roller coaster of spring, right? Cold, hot, cold, hot.
Yeah, we got rain and hail yesterday.
Oh, fun. We just got a little bit of rain. Well, we're almost at the end of the semester. Can you believe it? So here's what's going to happen over the next week and a half. Next week is usually what would be our finals week, but we're not going to have a final exam. It's all based on the programs that you've done over the semester. So you're going to meet with me for about 5 minutes over Zoom. I've posted time slots for people to go sign up. So if you go read the instructions on how to sign up for a time slot, you can do so. I've got time slots in the morning, some afternoons, and actually a couple of evening time slots available. And prior to that meeting, there is a end of semester, it's called end of semester reflection survey, where you go back and look at the work that you've done, kind of tally up how many assignments you've finished, how many assignments you've completed, and then also answer some questions about how you think you did in the course and what grade you think that you earned. And then we'll look at that response to your survey and then arrive at a consensus about what grade I should ultimately submit to the admissions and records for your transcript. The thing to keep in mind is that if you look at your grade sheet, all the way at the bottom or at the right-hand side, depending upon how it's arranged on your screen, there's a thing that says like final grade or total. Don't look at that, right? That has really not much to do at all with your final grade, because nothing here is really worth anything. I mean, I have to put a 1 or a 0 to mark them as complete or incomplete, but really it ultimately boils down to what was the quality of your work, and how did you mature as a C programmer over the semester, and were you able to apply any of the concepts that we learned in the class outside of class? So those are the kinds of things I'm looking for. It's not just a raw how much stuff did you do, rather it's how much did you learn and how much did you improve over the semester. So try to avoid looking at that final score, because that's not the grade that we're going to assign. We're going to talk about it and then arrive at a consensus. If you have not finished the assignments between now and next week, this would be a good time to do so. But please, try not to throw them all at me at the last moment, because I have to look at them and I still have to mark them complete or incomplete. So be aware of my time as well. This is a hectic time for me because I have to meet with about 100 students in the course of a week. And so that's, looking at about 20 per day or more. In some case more, because some people sign up for a time slot and realize that they haven't quite finished all their work, so they sign up for another time slot. So I sometimes meet with some students 2 or 3 times during that week. So it's a busy week for me to be meeting with all these people over Zoom. Although the sign-up grid will assign you a unique Zoom ID for your appointment, please just use the one labeled for my office hours. It's easier for me to sit in one Zoom session all day rather than to be switching Zoom sessions every 10 minutes. So that's a little bit of a confusion for some students. So you ignore the Zoom ID that the sign-up grid gives you and use instead the one for the office hours. Okay, so that'll be all starting on Monday. If you have done all of your assignments and you think you're ready to go, then sign up for a slot on Monday or Tuesday and get it over with and get it out of the way. What I tend to find is that I get a few people on Monday, slightly more on Tuesday, and then by Friday I'm just packed in because everyone is waiting till the last moment. So if you can possibly get stuff done before at the beginning of the week, that would really save both of us a lot of time. Okay, so I think that's pretty much it for the rest of the semester. Today we're going to do a little bit about quantum computing. It's probably a topic that is interesting to some of you. Now, if you've been watching my YouTube streams and you watched, what was it, last Wednesday, we did quantum computing as well, but we all just did it on, we did the program in Python. Today we're going to do it in C, so I'll show you how to do that in the language that we've been studying. but the content's going to be pretty much the same as what I did for that other course. So I'm going to start off with a video for you to watch that gives you a brief introduction to what is quantum computing and the kinds of problems that it may be able to solve, and then we'll start talking about it from there. So, are there any questions before we get going? All right. Well, let's see if I can get this video playing, and I'll be back in about, I think it's about 10 minutes or so. Let's see. Here we go.
My name's Talia Gershon, and I'm a scientist at IBM Research. Today I've been challenged to explain a topic with 5 levels of increasing complexity. It's a completely different kind of computing called quantum computing.
Do that again. Let me get my keys. I have some macros here that run those things, but I forgot to take away the countdown. So let's do this again.
Hi, my name's Talia Gershon, and I'm a scientist at IBM Research. Today I've been challenged to explain a topic with 5 levels of increasing complexity. It's a completely different kind of computing called quantum computing. Quantum computers approach solving problems in a fundamentally new way. And we hope that by taking this new approach to computation, we'll be able to start exploring some problems that we could never solve any other way. Hopefully by the end of today, everyone can leave this discussion understanding quantum computing at some level.
What's this?
Yeah, what do you think that is?
Fancy chandelier.
I think so too. We jokingly call it the chandelier. That's real gold, you know. This is a quantum computer.
It's a quantum.
Yeah, it's a really special kind of computer.
What does it do?
It calculates things, but in a totally different way to how your computer calculates things. What do you think this is?
A.
Yeah. Do you know what your computer thinks that is?
0, 1.
This really specific combination of zeros and ones. Everything that your computer does, showing you Pink Panther videos on YouTube, calculating things, searching the internet, it does all of that with a really specific combination of zeros and ones, which is crazy, right? That would be like saying your computer only understands these quarters. For each quarter, you need to tell it that you're going to use heads, tails, and you assign it heads or tails. So I can switch between heads and tails, and I can switch the zeros and ones in my computer so that it represents what I want it to represent, like an A. And with quantum computers, we have new rules we get to use too. We can actually spin one of our quarters. So it doesn't have to choose just one or the other.
Can computers help you with your homework, your really hard homework?
Yeah, they can. Especially if doing your homework involves calculating something or finding information. But what if your homework was to discover something totally new? A lot of those discovery questions are much harder to solve using the computers we have today. So the reason we're building these kinds of computers is because we think that maybe one day they're going to do a lot of really important things, like help us understand nature better, maybe help us create new medicines to help people. What's your favorite kind of computer? Smartphone, tablet, regular, laptop, PC?
I've got to go with my iPhone.
So what do you do with your iPhone?
Social media, use it for studying.
Have you ever run out of space on your iPhone?
All the time.
Me too.
Yeah, always when I'm trying to take a photo.
So did you know that there are certain kinds of problems that computers sort of run out of space almost? Like you're trying to solve the problem, and just like how you run out of space on your iPhone when you're trying to take a picture, if you're trying to solve the problem, you just run out of space. And even if you have the world's biggest supercomputer, did you know that can still happen?
Wow.
So my team is working on building new kinds of computers altogether, ones that operate by a totally different set of rules. So do you know what that is?
I have no clue.
It's a quantum computer.
A what?
Have you ever heard of a quantum computer?
I haven't.
Have you ever heard of the word quantum?
No.
Okay, so quantum mechanics is a branch of science, just like any other branch of science. It's a branch of physics. It's the study of things that are either really, really small, really, really well isolated, or really, really cold. And this particular branch of science is something we're using to totally reimagine how computing works. So we're building totally new kinds of computers based on the laws of quantum mechanics. That's what a quantum computer is.
Huh.
I'm going to start by telling you about something called superposition. So I'm going to explain it using this giant penny.
Wow. Is that like worth 100 pennies?
I don't know what it's worth, but I can put it face up, right? And that's heads. I can put it face down, right? So at any given time, point in time, if I ask you, is my penny heads or tails, probably you could answer it, right?
Yeah.
Okay. But what if I spin the penny? So let's do it. Okay, so while it's spinning, is it heads or tails?
Heads.
While it's spinning,
Oh, I would know.
it's sort of a combination of heads and
Yeah,
tails,
yeah.
right? Would you say? So superposition is this idea that my penny is not just either heads or tails. It's in this state, which is a combination of heads and tails. And this quantum property is something that we can have in real physical objects in the world. So that's superposition. And the second thing that we'll talk about is called entanglement. So now I'm going to give you a penny. Wow! When we use the word entangled in everyday language, what do we mean?
That something's intertwined or...
Exactly, that there's two things that are connected in some way, and usually we can separate them again.
Yeah.
If your hair is tangled or whatever, you can unentangle it, right?
Yeah.
But in the quantum world, when we entangle things, they're really now connected. It's much, much harder to separate them again. So using the same analogy, we spin our pennies and eventually they both stop, right? And when they stop, it's either heads or tails, right? So in my case, I got tails and you got heads. You see how they're totally disconnected from each other, right? Our pennies in the real world. Now, if our pennies were entangled and we both spun them together, right? When we stop them, if you measured your penny to be a head, I would measure my penny to be a head. And if you measured your penny to be a tails, I would measure my penny to be a tails. If we measured it at exactly the same time, we would still find that they were both exactly correlated.
That's crazy.
It's so cool, right?
Oh my god.
The way that we are able to actually see these quantum properties is by making our quantum chips really, really cold. So that's what this is all about, actually. This is called a dilution refrigerator, and it's a refrigerator. It doesn't look like a normal refrigerator, right? But it's something that we use, actually there's usually a case around it, to cool our quantum chips down cold enough that we can create superpositions and we can entangle qubits, and the information isn't lost to the environment.
Like, what could those chips be used to do?
So one of the things that we're trying to use quantum computers to do is simulating chemical bonding. Use a quantum system to model a quantum system.
Yeah, I mean, I'm definitely going to impress all my friends when I tell them about this. They're going to be like, quantum what?
So what do you think that thing is?
Is it some sort of conductor circuit?
That is a really good guess. There's parts of that that are definitely about conducting. This is the inside of a quantum computer.
Oh, wow.
Yeah, this whole infrastructure is all about creating levels that get progressively colder as you go from top to bottom down to the quantum chip, which is how we actually control the state of the qubits.
Oh, wow. So when you say colder, you mean like physically colder?
Yeah, like physically colder. So room temperature is 300 Kelvin. As you get down all the way to the bottom of the fridge, it's at 10 millikelvin.
Oh, wow.
Yeah. Amanda, what do you study?
So I'm studying computer science, currently a sophomore, and the track that I'm in is the intelligent systems track. Machine learning, artificial intelligence.
Have you ever heard of quantum computing?
From my understanding, with a quantum computer, rather than using transistors, is using spins. You can have superposition of spins, so different states. More combinations means more memory.
So that's pretty good. So you mentioned superposition, but you can also use other quantum properties like entanglement. Have you heard of entanglement?
I have not.
Okay, so it's this idea that you have two objects, and when you entangle them together, they become connected.
Oh, okay.
And then they're sort of permanently connected to each other, and they behave in ways that are sort of a system now. So superposition is one quantum property that we use. Entanglement is another quantum property, and a third is interference. How much do you know about interference?
Not much.
Okay, so how do noise-canceling headphones work?
They read like ambient wavelengths and then produce like the opposite one to cancel out.
They create interference. So you can have constructive interference and you can have destructive interference. If you have constructive interference, you have amplitudes, wave amplitudes that add, and so the signal gets larger. And if you have destructive interference, the amplitudes cancel. By using a property like interference, we can control quantum states and amplify the kinds of signals that are towards the right answer and then cancel the types of signals that are leading to the wrong answer. So given that you know that we're trying to use superposition, entanglement, and interference for computation, how do you think we build these computers?
I have no idea.
So step one is you need to be able to have an object or physical device, we call it a qubit or quantum bit, that can actually handle those things, can actually be put into superpositions of states. You know, 2 qubit states that you can physically entangle with each other. That's not really trivial, right? Things in our classical world, you can't really entangle things in our classical world so easily. We need to use devices where they can support a quantum state, and we can manipulate that quantum state. Atoms, ions, and in our case, superconducting qubits. We make qubits out of superconducting materials.
But as like a programmer, how would quantum computing affect a different way of writing a program?
It's a perfect question. I mean, it's very early for quantum computing, but we're building assembly languages. We're building layers of abstraction that are going to get you to a point as a programmer where you can interchangeably be programming something the way that you already do, and then make calls to a quantum computer so that you can bring it in when it makes sense. We're not envisioning quantum computers completely replacing classical computers anytime soon. We think that quantum computing is going to be used to accelerate the kinds of things that are really hard for classical machines.
So what exactly are some of those problems?
Simulating nature is something that's really hard, because if you take something like, you know, modeling atomic bonding and electronic orbital overlap, instead of now writing out a giant summation over many terms, you try and actually mimic the system you're trying to simulate directly on a quantum computer, which we can do for chemistry. And we're looking at ways of doing that for other types of things. There's a lot of exciting research right now on machine learning, trying to use quantum systems to accelerate machine learning problems.
So would it be like in 5 years or 10 years that I would be able to have like one of these sitting in my laptop just in my dorm?
I don't think you're going to have one in your dorm room anytime soon, but you'll have access to one. There's 3 free quantum computers that are all sitting in this lab here that anyone in the world can access through the cloud.
Okay, so quantum computing creates new possibilities and new ways to approach problems that classical computers have difficulty doing.
Couldn't have said it better myself.
So I'm a first-year master's student, and I'm studying machine learning. So it's in the computer science department, but it mixes computer science with math and probability and statistics.
So have you come up upon sort of any limits to machine learning?
Certainly, depending on the complexity of your model, then computational speed is one thing.
I have colleagues here that tell me it can take up to weeks to train certain neural networks, right?
Sure, yeah.
And actually, machine learning is one research direction where we're really hoping that we're going to find key parts of the machine learning computation that can be sped up using quantum computing.
Yeah, it's exciting. So in a classical computer, you have all sorts of logical gates that perform operations, and they change an input to some sort of output. But I guess it's not immediately obvious how you do that with quantum computers.
If you think about even just classical information like bits, right? At the end of the day, when you store a bit in your hard drive, there's a magnetic domain and you have a magnetic polarization, right?
Sure.
You can change the magnetization to be pointing up or pointing down, right? Quantum systems, we're still manipulating a device and changing the quantum state of that device. You can imagine if it's a spin, that you could have spin up and spin down,
Sure.
but you can also, if you isolate it enough, you can have a superposition of up and down.
Sure.
So what we do when we try to solve problems with a quantum computer is we encode parts of the problem we're trying to solve into a complex quantum state. And then we manipulate that state to drive it towards what will eventually represent the solution.
So how do we actually encode it to start with?
Yeah, that's a really good question. This actually is a model of the inside of one of our quantum computers.
Okay.
So you need a chip with qubits. Each qubit is a carrier of quantum information, and the way we control the state of that qubit is using microwave pulses. And you send them all the way down these cables, and we've calibrated these microwave pulses so that we know exactly this kind of pulse with this frequency and this duration will put the qubit into superposition, or will flip the state of the qubit from 0 to 1. Or if we apply a microwave pulse between 2 qubits, we can entangle them.
How do we measure
Yes, exactly, also through microwave signals.
it? Okay.
The key is to come up with algorithms where the result is deterministic.
Interesting. So what do those algorithms look like?
There's sort of 2 main classes of quantum algorithms. There's algorithms which were developed for decades, right? Things like Shor's algorithm, which is for factoring, Grover's algorithm for unstructured search, and these algorithms were designed assuming that you had a perfect fault-tolerant quantum computer, which is many decades away. So we're currently in a phase where we're exploring what can we do with these near-term quantum computers. And the answer is going to be, well, we need different kinds of algorithms to really even explore that question.
Yeah, certainly having a search algorithm is very useful. Factoring, those are definitely useful things that I would imagine could be done a lot faster on a quantum computer.
Yeah. They also unfortunately require fault tolerance. Right now, the algorithms that we know of today to do those things on a quantum computer require you to have millions of error-corrected qubits. Today we're at like 50, and it's actually amazing that we're at 50. There's things that we know or we have strong reason to believe are going to be faster to do on a quantum computer. And then there's things that we'll discover just by virtue of having one.
Sure. How could someone like me who's a grad student get involved in this, or what kinds of challenges are you facing that someone like me could help out with?
I'm glad you're interested. I think the place where lots of people can get involved right now is by going and trying it out and thinking about what they could do with it. There's a lot of opportunity to find these near-term applications that are only going to be found by trying things out.
I'm going to stop it there, because I think it gives you the gist of what the video is about. Are there any questions before we dive into some material that's related to the course that we're doing?
No specific questions, but it's a very interesting topic, and I'm sure that's just scratching the surface.
Oh, absolutely.
Like they talk about these concepts, and I don't really understand what they are. But
I'd have to say that the state of quantum computing now, here in the year 2022, is roughly where standard modern computing was back in the 1940s and 1950s. You may have heard that computers back then were these giant machines that filled most or all of a room and required huge power supplies and cooling facilities. And they only had a few bytes of memory to work with. They could only do really the kind of computations that a little $2 calculator can do. But they were the start of things. Back then, if you wanted to program one of those large, like ENIAC computers, you probably needed an electrical engineering degree, because it was built out of vacuum tubes and huge wires, and you had to physically connect the pieces together. And that's kind of where we are right now with quantum computers. They're these huge machines that require lots of cooling. You saw in the video that they have to cool it down to almost absolute zero. And then, you need things like microwaves to program the computer, and it's really kind of just the beginnings of it. But with the rate of technology, you could see maybe that the sizes of them will start shrinking down, the applications of them will start coming out, and maybe, and I'm not a fortune teller here, but maybe in 10, 20 years, it'll be much more commonplace now than it is now. And computer scientists will have invented things like programming languages and ways to use quantum computers that don't require an electrical engineering degree. Just like right now, you don't need an advanced degree in physics or engineering or electronics to be able to program a computer. You need a little bit about math, right? But, that's probably about it. And you can get by with, not much math, not much more than just arithmetic. So the reason why I'm kind of bringing it up now is I think that a lot of people who are currently going through a computer science degree and earning the 4-year degree or going up to a master's or a PhD should probably start thinking about, is this a wave that I want to be on top of? Because once quantum computers become a lot more mainstream and a lot more commonplace, and we're not there right now, but like I said, maybe 10, 20 years, then have you positioned yourself so that if you've got some expertise in the field, you can take advantage of that? So that's kind of my purpose in bringing it up right now, is just kind of get you thinking about it. If you want to start studying quantum computing, what should you do? I mean, how can you prepare yourself? At this point, most quantum computing courses are going to be found at the upper division, which is like 3rd and 4th year for a 4-year degree, or possibly also the graduate level. But what can you do to prepare yourself for those types of courses? I would think about maybe taking one of the physics courses in quantum mechanics. If only just to get the kind of surface level understanding of what's going on in these quantum particles that are interacting with each other. And also definitely pay attention in your linear algebra class, if only to get the unit on doing matrix multiplication and matrix arithmetic. Because in classical computing, the arithmetic is just done with things like plus and minus and times. You're really not doing anything more than just basic operations. But in the quantum world, you're doing all these calculations in 2 and 3 dimensions because the quantum particles exist in 2 or 3 dimensions. And so you need a way to represent these pieces of information in those multi-dimensional ways. And that's where matrices come in. So let's talk a little bit about what's the difference between classical computing and quantum computing. So in a classical computer, our fundamental unit of operation, your fundamental unit of storage is what we call a bit. But now we have to call it a classical bit versus a quantum bit because there's 2 kinds now. A classical bit is either a 0 or 1. And in the video, they represented that with like heads or tails on a coin. And we know for a coin or a bit that it's either going to be heads or it's going to be tails. At least that's what we call it in the United States, right? Heads is the side of the coin with the person's face, and tails is the other side. I think some countries call it, the front and the back of the coin. Anyway, but we know from a coin that it will never be both, right? Or never be neither. It's always going to be either heads or tails, assuming the coin can only be in these 2 directions, that it can't land on its edge. But for a quantum bit, which is called a qubit, you represent that using some kind of quantum particle, like an electron or a photon or maybe an atom with energy states. And if you think back to chemistry or physics class you might have taken in high school, this is a very poor representation of an atom, but you basically got a nucleus where the protons and neutrons are kept, and then orbiting around the nucleus is 1 or more electrons. And depending upon how much, and this is just one way to represent a qubit. It's not the only way, but it's just one way to do it. Depending upon how much energy that atom has, the electron might be in an inner orbit or it might be in an outer orbit. So if the electron has more energy, it might flip to an outer orbit. And then once it loses that energy, it might come down to an inner orbit. But the interesting thing about electrons is that it's never like in the middle. It's kind of weird. It snaps back and forth between this outer orbit and inner orbit. This is very different from what we humans experience. If you are like, let's say, swinging something around you on a rope, and then you bring that rope in so that thing's in a smaller circle, right? That object that you're swinging around has to occupy the space in between those 2 orbits. But on electrons, they don't. It just snaps back and forth between these 2 energy states instantaneously, and it never occupies that space in the middle. Well, so that's kind of weird, but we can take advantage of that because we know that the electron is going to be in this outer orbit or this inner orbit, but not like in the middle. And that gives us our 0 and 1. But quantum particles can exist in this weird state called superposition, and that's kind of like the spinning coin. And if I was to take this coin and start spinning it, you couldn't tell me for sure whether it was going to be heads or tails, but you would be able to assign probabilities to it. You could say, well, once this coin stops, there's a 50% chance it'll be heads, and it'll be 50% chance it'll be tails, but I won't know until the coin stops. Or what I could do is I could use a camera and I could take a picture of the coin as it's spinning. But the moment that picture is taken, it's either going to be heads or tails. And this is where the analogy breaks down a little bit, because in the real world, you might take a picture of it and it might be, halfway between heads and tails. But remember, in the quantum world, it's either heads or tails. You just don't know whether it's heads or tails until you look at it. So that's roughly what superposition is. It's a kind of this unknown state with some probabilities assigned to each of the states. So 50% heads, 50% tails, or you might have a coin that is weighted to one or the other. You might say it's got a 60% chance of being heads and 40% chance of being tails. And then when you take a picture of it over and over again, sure enough, you see 6 out of 10 times you take a picture of it and it comes up heads, and 4 out of 10 times it comes up tails. So the interesting thing about quantum particles is when they're in this superposition state, you don't know which one they are, but the moment you take a look at them, what's called the wave function collapses down and it becomes one or the other. Okay, so that's kind of my bird's eye view of how to store a quantum bit. And as you can imagine, it's not easy to store one of these bits. You saw that, what they call the chandelier, right? That makes the quantum bits really cold, and down into that chip is where they store just like 1 or 2 of these quantum bits. And so they basically trapped a quantum particle in one of those chips, and then they can manipulate it. They can make it, and it's usually done with spin. They can make it spin in this direction or this direction. That can change the 1 or 0 state. And it actually does exist in 3 dimensions because it can spin this way, or this way, or this way. And they can control all those spins using these, I don't understand it, right? Microwave energies somehow. So we could play a simple game. So imagine we start with a coin, and we'll start it with heads showing. And then this will be a game that you play against 2 people, or it could be a computer and a person. So the first person, or the computer, decides whether or not to turn the coin over. So not to like flip it, right? But just to either keep it at heads or decide to flip it over to tails. And then they pass the coin to the person, and then the person, the human, can also decide whether or not to invert the coin. And then finally you pass it back to the computer or the first person, and then that person also can decide whether or not to invert the coin. And then you look at the coin, and if the coin is heads, then the first player or the computer wins, and if the coin is tails, then the second player or the human wins. Okay, so simple game. It's just up to 3 possible coin inversions. And so you can make a prediction about who you think is going to win any particular game. And you might think, well, sounds like there's a lot of random possibilities in there. It's probably going to be about 50-50. But let's write a computer program to play this game. So I'm going to start out by defining heads to be 0 and tails to be 1. And I'm going to need a function here that basically randomly decides something, randomly decides whether to invert the coin or not. So let's make a function called decide. And all this one is going to do is just randomly pick between 2 states. Let's make it 0 or 1. So it's going to return 0 or 1, basically. So let's see, we're going to return random mod 2. Okay, so that'll return either 0 or 1. So in our main, we're going to need to initialize the random number generator. And now we'll play the game. Oh, let's make a function called game. So in this game, we are going to randomly decide whether or not to flip the coin. So let's start the coin out at heads. Value is 0. And then we'll say if decide. So if that's true, then just simply invert the coin. And then the user, the human, decides whether or not to flip the coin. So we'll pass that in as a parameter. And then finally, the computer decides whether or not to flip the coin. And then we'll return, after the game is done, what state the coin is in, either heads or tails. So this will play one game. So initialize the coin to heads, then the computer randomly decides whether or not to flip the coin. Then the user decides whether or not to flip the coin, and then finally the computer decides whether or not to flip the coin, and then we just return the coin. So in our main here, let's keep track of the scores, and then we'll play the game. Let's play the game, let's say 100 times. So we'll play the game, and let's initially, we'll play the game, and then we'll fill this in here in just a moment. And then we'll say if result equals heads, then the computer won one of the games. Otherwise, the user won one of the games. And then when we're all done with 100 turns, we'll print out the score. Okay, so just to recap here, we've got a function that does a random decision about whether or not to do something. We've got a game that initializes the coin to heads and then plays the game, returning what the coin is at the end of the game. And then we got a main that plays the game 100 times and then tallies the results of each game. So let's initially decide perhaps that the user is not going to flip the coin. And we can say that the user won 57 times and the computer won 43 times. And if we do that again, now it's 56 and 44. Do that again, 53, 47, 45, 55. So you can see, you know, if we were to do this more a whole bunch of times, in fact, let's do it 1,000 times. Let's just go for, yeah, we can see it's pretty close to 50-50. And then if we decide, yes, we are going to flip the coin each time, then again, you know, roughly 50-50. And we could, in fact, randomly decide whether or not to flip the coin. And again, pretty close to 50-50. So if we were to play this game in the real world, you know, it'd be about even odds about whether the computer is going to win or whether the human is going to win. So we'll come back to that game here in just a little bit. A classical bit we represent with either 0 or 1. A qubit, we use this notation to represent a qubit. It's a vertical bar, then either a 0 or a 1, and then a greater than sign. But a qubit doesn't exist as either a 0 or a 1. It can exist in that superposition, which means it's kind of like on this, this spectrum, if you will, where it could be kind of like anywhere in here. If it's right in the middle, then we can say there's a 50-50 chance it's either a 0 or 1. If it's kind of like towards this end, there's a greater chance that it's a 0. And if it's over on this end, there's a greater chance that it's a 1. But it's, you know, it's somewhere in here. It's more convenient from a computational, a mathematical point of view if we represent the qubit state not on a single axis like this, but actually on a two-dimensional axis. So we can draw it, put it over here, we can draw it like this. So we'll use 2D axes, and we'll draw on that axis a unit circle. The unit circle is basically a circle of radius 1. So here's the circle. And we can think of the vertical axis as being the one direction, and the horizontal axis as being the 0 direction. Or since this qubit exists in a two-dimensional space, we can think of the vertical direction as being like maybe its spin direction vertically, and the horizontal direction on the axis as being its spin direction horizontally. To tell you the truth, it actually exists in a three-dimensional space, so it's on a sphere, and more advanced quantum computations will actually use the three-dimensional model of the qubit, but it's okay to start with just a two-dimensional flat disk. So there's some interesting spots on this unit circle. There's this one over here on the right-hand side, and that one represents the 0 state. So its Cartesian coordinates are 1, 0. The first number is the coordinate in the x direction, and the second number is the coordinate in the y direction. And then there's another interesting point, and that's up here at the top, and the Cartesian coordinates are 0, 1 on that. So we can also represent those points not as a tuple, a pair of numbers, but as a matrix. And if you've not taken linear algebra, don't worry about it. I'll show you just enough to be able to get your toes wet. But basically a matrix is kind of like an array of numbers represented inside of square brackets. And we're going to represent these vertically. And this is just a different way of representing exactly the same information. So we've got 3 ways to represent those 2 points on this unit circle. Okay, so in a classical bit, we have some of the fundamental operations that act on it. Things like and, or, not, exclusive or, add, subtract. Let's talk about a couple of those. The first one we're going to talk about is not. This one's really simple. If you take a classical 0-bit, oops, I didn't mean to put X there, I meant to put not. If you take a classical 0-bit and you apply the not operation to it, you'll get a 1. And if you take a classical 1-bit and apply the not operation to it, you'll get a 0. And this is really the definition of what not is. It's a truth table that says if you feed in a 0, you'll get a 1, and if you feed in a 1, you'll get a 0. So in quantum bits, you also have a not operation, and it's represented by the letter X. Or sometimes it's also represented with the circle with a little plus in it. But if you take a quantum 0-bit and you apply the not operation to it, you should get the quantum 1-bit. And if you apply the quantum not operation to the 1-bit, you'll get a 0. I mean, that's the definition of what not is. It takes the quantum bit and it basically flips it to the other position. Now, in classical bits, the not operation is represented with a truth table. In quantum computations, it's represented also with a matrix. The X matrix is 0, 1, 1, 0. So if we apply the X operation to the 0 quantum bit, this is really just a multiplication. We're taking this matrix, the X matrix, and multiplying it by the 0 quantum matrix. So we're doing this. 0, 1, 1, 0 times 1, 0. So we're multiplying those two matrices together. So let me show you how to multiply matrices together. If you have a 2 by 2 matrix and you want to multiply it by a 1 by 2 matrix, here's how you calculate the answer. You take the upper left number multiplied by the top number plus the upper right number multiplied by the lower number. That's this one here. And then the other result is the lower left number multiplied by the top number plus the lower right number multiplied by the bottom number. That's this one here. So you'll get a matrix out of it that is one column with two values in it. Okay, so we're doing this calculation. 0, 1, 1, 0 times 1, 0. All right, so let's do it. 0 times 1 plus 1 times 0. And then for the bottom, we got 1 times 1 plus 0 times 0. So that gives us 0 plus 0 on the top and 1 plus 0 on the bottom. Which is just 0, 1. And that's exactly what we wanted. If we start with the 0 qubit and apply the NOT operation to it, we'll get the 1 qubit. And then same thing happens for the 1 qubit. 0 times 0 plus 1 times 1 over 1 times 0 plus 0 times 1. And then we get 0 plus 1 on the top and 0 plus 0 on the bottom, which gives us 1, 0, which is the 0 qubit. So I want to point out that this is not like a fundamental property of quantum bits and atoms. This was basically the mathematicians and the computer scientists and the physicists who wanted to invent quantum computers. And these were thought of decades ago, long before quantum computers were ever actually built. So the first quantum computers were only built within the last 10 years, maybe even less than that. But all of these things were devised or thought about decades ago in the 1950s, when they had first kind of discovered about the power of atoms and electrons and things like that. And so they set about to say, like, well, what are the fundamental operations that we want these quantum computers to do? And so we've got NOT, and we've got the H operation, which I'll show you in a little minute, and there's the C NOT operation, which is kind of like exclusive OR. So they came up with all these fundamental operations. Just like in a standard computer, we got the fundamental ANDs and ORs and NOTs and exclusive ORs. They came up with all these fundamental operations and said, well, what's the mathematical model that will help describe how these operations should work? So they came up with what I just showed you here on the screen. And then they said, well, if a quantum computer is ever actually built, this is what it should do. It should have some kind of like way to trap a quantum particle in a state of either 0 or 1, and then a way to flip it from 0 to 1 or 1 to 0. So we're not kind of discovering fundamental operations on atoms. What we're doing is designing a machine that makes the atoms behave this way. Just like in a classical computer, ones and zeros are not fundamental properties of electricity. It kind of is, but not really. What we did is we designed computers to do these operations that we want them to do. We want them to be able to add, and we want them to be able to multiply and compare. So we designed a computer to do those operations rather than just like, let's throw some wires together and just see what happens, right? So that was something that I kind of had to get my head around when I was learning about quantum computing, is that we're not kind of exploring the nature of atoms. We are designing a computer to do what we want it to do. And what I showed you on the screen is what we want it to do when we flip from 0 to 1 or 1 to 0. So since this is a programming a class in C programming, let's make a program to simulate or to do this calculation. I put quantum.com. That's crazy there. So we're going to need something to represent a qubit. And I think a structure would work here really well. We can represent a qubit as being two floating point numbers. Because we're on a unit circle, basically the qubit can be anywhere on that circle, which means it's not going to be just integers. It's going to be floating point numbers. So we'll go float, let's just call it float x. One of those will use x. And so in my main, I want to be able to do this. I want to go struct qubit. Let's call it, I don't know, q. And we can assign to q the values 1 and 0. Actually, we'll do 1.0 and 0.0. And then I want to apply the not operation to that. So we'll go, let's do struct qubit result equals, and let's call it q naught, right? Quantum naught. We'll pass in q, and we'll get a result, and then we'll just print it out. So let's make a function here called void print qubit. Actually, I'll use it using parentheses. And then we'll go q.x and q.y. All right, so then we'll say print qubit, and we'll pass in the result. And if this works, we should see 0, 1 be displayed. Okay, so we need a function that does q naught. I'll call it Q. All right, so this needs to implement this calculation right here. So let's create a new qubit, and let's call it R, our result. And then we can calculate the x value of the R and the y value of R. So R.x is equal to, see, here's our calculation. It is going to be 0 times whatever the x value of the qubit that we're calculating, and plus 1 times the y value. So 0 times q.x plus 1 times q.y. And then the y value of our result is going to be 1 times q dot x plus 0 times q dot y. And then we'll just return the resulting qubit. Okay, so we're going to start with a qubit in the 0 state. Then we're going to apply the quantum NOT operation to it and get a resulting answer, and then we'll just print out that answer. And there we go. We got 0 and 1, which is exactly what we wanted. And then if I take the let's take that result and let's apply the quantum NOT operation to it. So result equals Q naught result. We should now get it back to the state it was in. And it's good. So we applied the quantum NOT to it, it got 0, 1. And then we applied quantum NOT to it again, and we got 1, 0. So it seems like our NOT operation is working. And so what we're writing here is basically a simulator of a quantum computer. Now, IBM has been one of the leaders in doing quantum computing, and they've actually made their quantum computers available for anyone to use. All you need to do is sign up for an account, and you can put in some very simple programs on their computer. Let's go ahead and do that. So I've already got an account on here, and we're going to now launch the composer.
We're not seeing your screen.
Oh, sorry. So what we've got here is kind of the list of the operations that we can do. Here's the one we're doing right now, the NOT gate. And then later on, we're going to do this H gate here, but we're going to start with the NOT gate. And we have at our disposal 3 quantum bits that we can play with. Q0, Q1, and Q2. So if we start Q0 out at the 0 state, and then we apply the NOT operation to it, and then we measure it. It's running it now on a little simulator here, but it says that 100% of the time we should get the answer 0, 0, 1. So qubit 2 will be a 0, but we're actually not going to be using this one. Let's just throw it away. Throw that one away. We'll throw that one away. There we go. So 100% of the time, we're going to end up in a 1 state. So we started out at 0, we applied the NOT operation, and then we ended up in the 1 state. And if we actually put another NOT in there, let's squeeze one in, we can see that it flips back to be the 0 state. So this is actually not running on a real quantum computer right now. This is just a simulator, basically doing the computation that we just wrote a program for. But we could click on Set Up and Run, and it will queue up the job and run it on one of their actual quantum computers, which looks like one of those chandeliers that you saw in the video, and we'd get a result. We'd have to wait a couple minutes because there's other people using the quantum computers at the same time. But we would actually get the results. Okay, so that's the NOT operation. Let me go and fetch this nice little diagram that we're making. So on this unit circle, there's a couple of other interesting spots. There's one right here that's halfway in between the 0 and 1 state. This is called the plus state. And its Cartesian coordinates are, well, here's where we need to use a little bit of trigonometry or algebra. No, not algebra, geometry. This is a little right triangle, and its interior angle here is 45 degrees. And we want to know, what are the Cartesian coordinates of that point? Well, this distance right here is 1 over the square root of 2, and so is that y distance. So this is 1 over root 2, comma, 1 over root 2, which can also be represented vertically as 1 over root 2, 1 over root 2, and that's what we define the plus state to be. So you can think of that plus state as being the superposition state. It's not a 0, it's not a 1, it's midway between. So there's a 50-50 chance that when we actually look at the qubit, it'll be a 0 or a 1. But we won't know until we look at it. So one of the fundamental operations of a quantum computer is called the Hadamard operation, or just H. The purpose of the H operation is to take a qubit, let's say here's the one in the 0 position, and put it into the plus position. You can actually take a qubit and put it into a superposition state where it's neither a 0 nor a 1. And just like with the NOT gate, the H operation is represented with a matrix. I've learned in quantum computing you get to write 1 over root 2 a lot. I'm sure at some point someone will invent some symbol that we can just use to represent that, like R or something like that. And then we don't have to keep writing it over and over again. Okay, in case you're wondering about this, if you have a matrix of numbers and then you have a constant out in front, all you do is you multiply that constant by each one of the values in the matrix, and that's what you get. Okay, so if we take the Hadamard operation and apply it to the 0 qubit, what we should find is that it starts here at 0 and then it kind of rotates it up into that plus position. And just like with the NOT, all we have to do is multiply these two matrices together, and we should get our answer. So let's try it out. So we're going to multiply top left times top plus top right times bottom, and then bottom left times top, and then bottom right times bottom. And since this is a negative, we're actually going to do minus instead of plus. All right, let's simplify this. We get 1 over root 2 plus 0, and then 1 over root 2 minus 0. Which is 1 over root 2, 1 over root 2, which is exactly what we wanted. So if we take the 0 qubit and we apply the Hadamard operation to it, it will put that qubit into superposition where it's neither a 0 nor a 1. And if we look back at the IBM computer, go ahead and do that. Well, let's see. Let's get rid of this one, and we'll get rid of this one, and we'll just slip in that H operation right here. We can see that according to the simulator, there's a 50-50 chance that it's either a 0 or a 1, with some slight deviations from 50-50 because The quantum computer at this point is not perfect. And they've simulated that imperfection, because although we can cool it down to almost absolute zero, we can't actually cool it down to all the way to absolute zero. So there's always going to be a little bit of stray energy in the system, which is going to cause the results not to be exactly what we wanted, but pretty close. Okay, so the Hadamard operation takes a 0 quantum bit and puts it into superposition where it's neither a 0 nor a 1. It's kind of both. So let's program that in. Let's just call it H. R dot X equals, and this is where I could really use a define to help me out. Let's call this, let's call it R. All right. What is 1 over root 2? 1 divided by the square root of 2 is 0.707106. 7812. Actually, let's do this. Include math.h. 1 divided by square root of 2.0. I'll call this R2. So R2 times R point X plus R2 times R dot Y, and then R dot Y is equal to R2 times R dot X minus R2 times R dot Y. And we'll return R. Change our program so that we start the qubit out in the 0 state. We'll apply the H operation to it and see what we get. That's not what I expected. What happened here?
It needs to be Q on the right side of those two operations.
Thank you.
Q dot X and Q dot Y.
I'm just computing the result of itself. There we go. Thank you. There we go. So that's, each one of those is 1 over root 2. So what do you think is going to happen if we apply the Hadamard operation to the plus state? Right? It's here in the superposition. What's going to happen if we apply the H operation to itself? Actually, I won't do that. I won't do it like that. Let's just flip this around. Oh no, I meant to do R2, R2. Okay, so the qubit Q starts in the plus position, and then we apply the Hadamard operation. What are we going to get? What is that? All right, so we took a qubit that was in the plus superposition, we applied the Hadamard operation to it, and we printed it out, and we got 1, 0. What is that? So let's work it out. 1 over root 2 times 1 over root 2 plus 1 over root 2 times 1 over root 2. And then on the bottom, we have 1 over root 2 times 1 over root 2 minus 1 over root 2 times 1 over root 2. 1 over root 2 times 1 over root 2 is 1/2.
We can't see your scratch work.
Oh, I'm so sorry.
Thanks.
I'm just working out the matrix multiplication here. So we ended up with 1/2 plus 1/2 on the top, and then 1/2 minus 1/2 on the bottom, which is 1, 0, which is the 0 qubit. So that's really interesting. If you apply the Hadamard operation to a qubit that's in the superposition state, it flips back to the 0 state. So you can think of these operations as being kind of like this state machine where you've got the state 0 and the state 1 and the plus state. And if you apply the X or not operation to the 0 state, you end up in the 1 state. And if you apply the X operation to the 1, you end up in the 0. That makes sense. And then if you apply the H operation to the 0, you get the plus state. And if you apply the H operation to the 1, you get, if you apply the H operation to the plus state, you go back to 0. So the Hadamard operator takes a qubit and puts it into superposition or takes it out of superposition. It's kind of like a little toggle. Okay, so let's try that out. Oh, we already, let's see, what did we tried? Plus, yeah, we already did this. All right, so we started a qubit in the plus position, and we saw that it came out to be the 0 qubit. So what happens if we apply the H operation, not the H operation, the X operation to the plus qubit? We already know what happens when we apply it to the 0 and the 1, but what happens when we apply it to the plus? So we already know that the X operation is represented by this matrix, and plus is 1 over root 2, 1 over root 2. So we get 0 times 1 over root 2 plus 1 times 1 over root 2. And then 1 times 1 over root 2 plus 0 times 1 over root 2. And we get 0 plus 1 over root 2 on the top, and 1 over root 2 plus 0, which is 1 over root 2, 1 over root 2, which is the plus. Okay, interesting. So let's complete this state machine, state diagram. So X applied to 0 takes us to 1, and X applied to 1 takes us to 0. H applied to 0 takes us to plus, and H applied to plus takes us back to 0, and X applied to plus takes us back to ourself. So if we apply the not operator to a qubit that's in superposition, it stays in superposition. Maybe you can think of kind of like pouring two colors of paint into a paint can. And the Hadamard operator stirs the paint can, so now the two colors are blended together. If you then give it an extra stir, they're still blended together. You haven't really changed anything. But the cool thing about this paint can is that if I then like stir it in the other direction, the paint colors will unblend themselves and go back to being what they were before. That's one of the strangenesses of quantum properties. So let's go back and play that simple game that we were talking about. Remember that coin flip game, where either the computer can decide whether or not to flip the coin, and then the user will decide whether or not to flip the coin, and then the computer will decide whether or not to flip the coin, and then we see what it is. So in this case, flipping the coin is the X operation, but the computer is going to cheat a little bit. The computer is going to use the Hadamard operator to put the coin into superposition. So we'll start the qubit out at 0, which represents heads. The computer will then decide or not whether to flip the coin by putting it into superposition. So now the coin is kind of like in both. We don't know which one it is because we haven't looked at it. And then let's say we decide to flip the coin, and then the computer then plays its move and applies the Hadamard operator again, and we can see that 100% of the time the coin ends up in heads. So because we're playing on a quantum computer and the computer is cheating a little bit, the coin always comes out in favor of the computer. So that's if we decide to flip the coin in the middle. And then if we decide not to flip the coin, if we just say delete that, it doesn't change the outcome. So the computer always wins this particular game. And the important thing here is this Hadamard operator puts the coin into superposition so that we can't see whether it's heads or tails. The computer actually can't see either. It just puts it into this state where it's neither heads nor tails. There's a 50-50 chance that it's one or the other. Applying that not operator in the middle doesn't change the outcome. But then that final Hadamard operator flips it back to the 0 position, and then the computer always wins. So here's that coin flip game again. So we start out in heads. We apply the Hadamard operator, which means we are now in the plus position. And then as we saw, if we do the X operator on that, we still stay in the plus position. And then finally this takes us to, the final Hadamard takes us back to the 0 position. And then if we decide not to do the X, we still go to the plus, and then the final Hadamard takes us back to 0. So either way, the computer is going to win. So, I mean, that's all like fun and games, but what can a quantum computer actually do for us? So again, there's been some algorithms that were invented before quantum computers were actually created. One of the important ones is called Grover's algorithm. And Grover's algorithm is one that can search for some particular criteria that you are seeking. For example, if we were to write a program to look through an array of numbers, an array of unsorted numbers, and we want to find out which one is the biggest, then we would write a loop that starts at the first number and iterates through the entire array, keeping track of which one was the biggest one we'd seen so far. By the time we got to the end, we would have our answer. We would know what the maximum number is. But the important thing there is that we would have to look at every element of the array in order to figure out which one was the biggest. So an array of size n, we have to look at n elements of the array to figure out which one is the biggest one. We can say that the size of the problem increases linearly with the size of the number of elements. The number of elements we have to look at increases in proportion with the size of the array. Now I'm going to give you a very shallow view of what Grover's algorithm is. In Grover's algorithm, you kind of picture it like this. You have, let's say you have 100 elements in your array. What you do is you assign each one of those elements to be a qubit. So qubit number 0 represents element number 0 in the array. Qubit number 1 represents element number 1 in the array. And a qubit is either a 0 or a 1. And we'll say that it's a 0 if that particular qubit's representation is not the biggest number, and it's a 1 if it is the biggest number. Think of it as being 100 people in a room, and they can either sit or stand. So you start everyone out standing, and then you say, or you start everyone else sitting, doesn't matter. Either they're all sitting or they're all standing, and you make an announcement. You say like, okay, if you, and let's say their ages, like if you are the oldest person in the room, stand up. And so you make that announcement to all 100 people simultaneously. And what are they going to do? Right? You've given them that simple instruction. If you are the oldest person in the room, stand up. And of course, let's assume that they can't look at each other and know what their ages are based upon their appearance, right? Everyone looks identical. Or maybe it's like if I don't know, if you have the oldest car, right? Stand up. So what do? Right? They kind of like look at each other and go like, I don't know if I'm the oldest person, but I guess I'm the oldest person, so I'll stand up. So after one iteration of this, a few of the people are standing up and most of them have sat down. And so you make that announcement again. You know, of the people who are still standing, if you are the oldest person or you have the oldest car, please remain standing, otherwise sit down. And so a few people standing will like look around and go, okay, well, I guess I don't have the oldest car, so I'll sit down. And you repeat that process several times. And at the end of it, you will only have one person standing, and they will have that'll be the person that represents the one with the oldest car or the oldest person. It's kind of a strange thing to do, right? You just make this announcement, and then you just kind of like let them do their thing a few times, and then you'll get your answer. It's pretty strange. And it turns out that the number of times you have to do this iteration is proportional to the square root of the number of elements. So if you have a room full of 100 people, you only have to do this 10 times. And then you'll have the one person who's the oldest or represents the oldest car standing up, and everyone else will have sat down. It's kind of strange. But that's basically how a quantum algorithm like that would work, is you can have all these qubits kind of simultaneously working on the problem. So what you do is you start everyone out, you initialize all of the qubits to be in the superposition state. So you don't know whether they are the oldest person or not. And then you tell them, if you are the oldest person, stay standing. So put yourself into 1 state. And if you are not, put yourself into 0 state. And you just do that the square root of n times. And yet at the end of that, you're guaranteed to have only one of them standing. And that will be the answer. How bizarre is that? So that's basically what Grover's algorithm is. So it's kind of like a wrapper, right? You have this engine that's querying the qubits a square root of n number of times, and then you have this little step in the middle where each of the qubits basically evaluates whether or not it's the oldest one or not. And then it changes itself to a 1 if it is, and it changes itself to a 0 if it's not. All you have to do to adapt this algorithm to any kind of criteria is just change that one little piece. Here's roughly what Grover's algorithm looks like. So you initialize everyone to be in the Hadamard state, and then you start rolling the algorithm forward. And then at the end, you just measure which one is still standing up, and then you've got your answer. I don't remember what this one, which criteria this one is particularly looking for, but right here in the middle somewhere is the actual evaluation of a function that determines whether or not this one is the tallest or not, or whatever criteria I'm looking for. So that's Grover's algorithm. And then there's another one called Shor's algorithm, and this one is used to factor numbers. It works kind of like the same way that Grover's does, is that you've got qubits that represent all the possible factors of a number. So let's say you're trying to factor the number 15. So you'd start out with 15 qubits, each one of them representing one of the possible factors. So one represents 1, one represents 2, one represents 3, and so forth. And then you kind of do the same thing. You say, like, if you are a factor of 15, stand up. If you are not, sit down. And you do that square root of n number of times, and at the end of it, you will have, in this case, 2 qubits still standing up, the one representing 5 and the one representing 3, and all the others will have sat down. So what does that mean for things like cryptography? So in standard classical cryptography, if you have a large number that is the product of 2 primes, it is known that this is a very difficult problem to solve. If you have a number that is known to be the product of 2 primes, finding those 2 prime numbers is very difficult. It's not impossible. You can just write a program that will try all the possible factors, and eventually you'll stumble across the 2 prime factors. But if the number is really big, let's say it's 2 or 3 or 400 digits long, it will take a very long time to factor that number, like age of the universe time, to factor that number into its 2 prime factors. But with Shor's algorithm, we could do it much more quickly. Not instantaneously quickly, but much more quickly than just trying all the possible factors. And so the upshot there is that if quantum computers become big enough that we could have, let's say, hundreds, thousands, millions of qubits at our disposal, we could potentially factor numbers pretty quickly, which means that all the current algorithms we have for doing cryptography on classical computers will become obsolete overnight. Now, before you start sweating, of course, we're not there yet, but the moment that happens, every cryptography algorithm we have will just not work anymore, because now people will be able to factor those numbers very quickly. What does that mean? That means that researchers, computer scientists and mathematicians need to start thinking now about what cryptography algorithms can we start using so that even a quantum computer can't solve that problem quickly. And that has to be ready to go the moment that powerful enough quantum computers become available, which might be in the next 10 or 20 years. And that's where you come in, right? Do you want to be one of those researchers that helps out solve this problem so that, as soon as we get a desktop-sized quantum computer that anyone can afford, that we have algorithms in place so that all of your transactions on the internet can be secured the moment that happens? So how big do these computers need to be? Well, there's this threshold that some scientists have kind of made up called the quantum supremacy threshold. And that is the point at which a quantum computer exceeds all the computational power of the entire planet. Let me see if I can summarize that. So one single bit can hold one of 2 values, either a 0 or a 1. 2 bits can hold one of 4 values, 0, 0, 0, 1, 1, 0, or 1, 1. Following me? So 3 bits can hold one of 8 possible values. But the important thing there is they can only represent 1 of 8, or 1 of 16, or 1 of 32. But a quantum bit can hold not only just a 1 or a 0, but also kind of like both, right, with some probability of being either a 0 or a 1. So one quantum bit can basically take the place of, one quantum bit can take the place of 2 classical bits. And 2 quantum bits can take the place of 4 classical bits. Because 2 quantum bits can hold 4 values simultaneously. 3 quantum bits can hold 8 values simultaneously. So once you get up to about 2 to the 60th or so, you're now holding 2 to the 60th values simultaneously. And that more or less exceeds the total computational power of all the computers on the planet combined. If you took all the bits of all the computers on the planet and you put them together, you could exceed that computational capacity if you had about 60 qubits at your disposal. And according to that video, we're already up to about 50, so it won't be long before we have quantum computers that can solve problems bigger than all the computational power of every computer on the planet put together. And all they need is like 60 qubits, and they can have more memory than all the computers put together. It's just, you know, and that's just like over the horizon. That's why it's really important, I think, for people like you to be, you know, up at the front of that wave that's going to happen, I think, pretty soon. You know, who knows? Maybe quantum computing will be like, okay, we got Grover algorithm, we got Shor's algorithm, we got a few more, and then what, right? And like that video pointed out, we have these algorithms now. What we need are people to start playing around with quantum computers and start envisioning, what could I do with this thing now that I have it? Like, nobody back in the 1940s and 50s would have predicted that what we spend most of our time using computers for is watching funny cat videos, playing games, and taking pictures of ourselves. And even that usage of computers didn't exist up until like the 1990s. So what will quantum computers bring? We don't know, because we're at the stage now, we're in the 1940s of quantum computing. It's going to take maybe 10, 20 years before we finally get some, wow, this is what we could really use quantum computers for. I mean, she talks about like simulating natural processes, right? Okay, but what's really going to be the killer application? What's going to be the thing that brings quantum computers to the forefront, where everyone needs one now because we can solve problems faster than we could before? Maybe everyone's going to need one because we'll need one to protect our internet transactions, right? Once the spies and the superpowers have all the quantum computers to break encryption, everyone's going to need one to be able to do encryption. Maybe that'll be the thing. So that's my little introduction to quantum computing. I took one of those free online courses through Coursera a couple of years ago to learn what I know now about quantum computing. I've pretty much told you what I know about. I know a little bit more, but once you start diving into it, the math gets a little more involved. You start needing derivatives and integrals. But it's one of those things where once you work out the computations, you really kind of don't need those anymore. Again, it's like standard computer science. Once you work out the truth tables, once you work out how transistors and electrons flow through the wires and the signals end up, you know, in the registers, you don't need that stuff anymore. You just program in high-level languages. In fact, you can see over here on the right-hand side, we have what is basically a Python program. So IBM has invented this thing called a QIS kit. And you write a Python program to represent your quantum program, and then you can submit that job to their quantum computer, or you can run it on your own computer in a simulator and see what the results are. So why not just simulate quantum computers on a regular computer? Again, it has to do with memory storage, right? So if you have 3 quantum bits, it takes 8? Is that right? 8 classical bits to represent that. If you have 100 quantum bits, it takes 2 to the 100th classical bits to represent that, and we just don't have that kind of computational power. So we can run the simulators pretty easily for a small number of qubits, but once the number of qubits goes up, then the number of classical bits needed to represent that goes exponentially up. And that's where you run into problems. Okay, well, like I said, that's pretty much what I know about quantum computing. And as you've seen, the mathematics behind it is fairly simple just to work out the results of the operations. The actual quantum computers have some more. There's this one here called the C0 gate, which is kind of similar to exclusive OR. The way this one works is you've got 2 qubits, and depending upon the state of one of them, it causes the other one to flip. So if one of the bits is called the controlling bit is a 1, it flips the other one from 1 to a 0 or a 0 to a 1. And if the controlling bit was a 0, it does not flip the other one. The cool thing about the C0 gate is that now you're taking 2 quantum bits and you're making the state of one of them depend upon the state of the other one. And that is done by entangling those 2 quantum bits together. Entanglement, and this is probably the last thing I'm going to bring up here. Entanglement is this weird quantum property where the state of one quantum particle can influence the state of another quantum particle. Imagine you've got one electron here in a low energy state, and when you cause it to flip maybe to a higher energy state, this one over here also flips to a higher energy state. And you didn't do anything to that second thing. It just somehow knew that the first one had changed. And scientists have shown that this entanglement actually works. What they did was they took some quantum particles, I think it was photons in this case, and they entangled pairs of photons together. So now you've got 2 photons that came from one, and you can actually go and you can buy, I forget what it's called, but it's basically a special crystal, and you shine a laser into it, and then it's like a prism, and then 2 laser lights come out of it, and those 2 laser lights have photons that are entangled with each other. So the one stream of photons goes in, and then 2 streams comes out, and the 2 streams are now entangled together. So it means that anything you do to one of the streams will affect the other stream. Kind of weird. What they did was they entangled these photons together, and then they put half of them on a rocket ship, and they launched it into space. And now it's orbiting the planet. And so on Earth, you have the one side of the pair of photons, and in space you have the other side, the entangled side. And they discovered and they proved that if you change the state of the photons down here on Earth, it'll change the ones in space. Now, the weird thing is there was no like transmission of information, right, from one to the other. There was no like radio signal that went from Earth up to that satellite that said, okay, change everyone. It's just, if you change them down here, they change up there. Right? Imagine what you could do with like communication over vast distances with something like this. Right now, if we want to communicate with some of our space probes that are way out there, like over by Jupiter and Pluto, it takes hours to send that signal out over space. And it takes hours for it to come back. And not only does it take time, it takes a lot of energy. We have to use some of our biggest radio telescopes to send that signal out. And then again, to listen for the very faint reply coming from that space probe out there. But imagine we could communicate with that space probe by just flipping some bits here on Earth, and then they flip over there on the space probe. Now, you're probably thinking, what about does it happen instantaneously? No, there's still a speed of light propagation time. So it still takes time for the information to get there, but we don't have to expend any extra energy to do so. All we have to do is just flip the bits down here on Earth, and they'll flip on the space probe over there, a couple hours later. And we didn't have to use one of these giant radio telescopes. That's like super cool weather, right? That we can now communicate over huge distances without expending extra energy to do so. All we have to do is entangle them together and then send one half of them on their way. How would you like to be on part of that? Right, imagine you could have Wi-Fi access and internet access without actually physically connecting a cable or without actually having radios in your computers, right? You just have entangled particles. It's like science fiction, but here. So, that's where we are right now, is exploring what we can do with these quantum computers. One of these days, I'm going to go buy one of those crystals. You can get them on eBay, I think. They're kind of expensive, a couple $100 for a small one. But then, like, does it actually work? Can I actually Can I shine? What you could do, I think, is you could take a laser light. You could polarize a laser light. You just use a standard polarizer, and then shine it into that crystal, and you'll get two beams that are both polarized in the same direction. And then I want to see if I then change the polarization of one, will it change the polarization of the other one? That'd be interesting to do. Okay, so that's basically it for quantum computing. If it seems strange and you don't quite understand what's going on, it probably means you're on your way to understanding it. Because scientists have just been baffled by the behavior of these quantum particles ever since they discovered that there's this weird behavior that they have that we don't as humans interact with on a day-to-day basis. But when you talk about the photons and the electrons and the neutrons and the gluons and all the other on things that happen at the subatomic level, then things get really weird. And you've got strange behaviors like particles that can communicate with each other without actually sending information back and forth, and particles that seem to go back in time and convey information to things that haven't happened yet. Plenty of YouTube videos out there. There's probably lots of YouTube videos that are completely fantastical and have no basis in reality, but there's some good ones out there about things like the quantum erasers, time erasers, and the two-slit experiment and other quantum properties that we're just now discovering and trying to take advantage of. Last YouTube comment here says, hopeful for this technology, but don't think the companies of today would give it to the public on the scale of traditional computers with no strings attached. You know, that's one of the things that, I don't know if it concerns me yet, but IBM has made their quantum computers available. And if you're a quantum researcher, a physicist, you can apply to them and they will give you access to more qubits simultaneously. As a free user, you get access to like 3 or 5 or 7, a pretty small number. But as a researcher, you can get like 10 or 12 of them. And then there's companies like Google and Microsoft and the large universities and some of the other large corporations, some of the financial corporations that also have their own quantum computers in their own private laboratories doing research. And, we don't really know what they're up to yet because they're all keeping that to themselves. They want that financial advantage of being the first to market with something. So what's Google doing with it? I'm not sure. I know they have a facility in Santa Barbara in conjunction with UC Santa Barbara. What's Microsoft doing? Don't know. What are places like Bank of America and Merrill Lynch and the New York Stock Exchange doing with them? I don't know. But they're doing something. So maybe you can get access to that kind of stuff if that's the kind of career path you want to go down. Well, so I think that's about it for today. For those of you in my class, finish up your assignments. Go on to Canvas and look for a slot that you can sign up for to talk with me next week for about 5 minutes. And we'll be back on Thursday, and we'll just kind of wrap up the whole semester, answer any questions you have, and then that'll be it. For those of you watching on YouTube, then we'll take a break for the summer. And I might do a few streams over the summer where I do some of the stuff with the retro 8-bit stuff I've got behind me. But otherwise, we'll be taking a break. Then we'll be back in the fall. I'll be back in the classroom for 1 or 2 of my classes. And my dream right now is to set up some cameras in there so that I can live stream those classes the way I've been live streaming these from my home. But that's a big project I got to work off over the summer, is getting some cameras in there and microphones and streaming equipment and so forth. I'll see if that comes out to be a reality. But that's where we are. Okay, Chris, any questions?
No, well, thank you very much. That was fascinating and
mind-blowing, and
it's mind-blowing. It's just a whole new world.
Yeah. And we want to be a part of it, I think.
Yeah.
All right.
All right. Well, thank you.
See you next time.
Bye.
All right, bye-bye. And those of you on YouTube who are watching, again, this is kind of the same material that we did last Wednesday, but you got to see the program being written in C rather than Python. So I hope you got something out of it, and I hope that maybe you think about pursuing or at least some line of study where you can learn a bit more about quantum computing. I think it's just fascinating stuff. And like I said, we don't really know what to do with it yet, but this is where you want to be, right? You want to be on the front of that wave so that when it does come, you'll be ready for it. So I think that's about it for today. We'll be back again on Wednesday and on Thursday with some more stuff. And then Friday or next week, we won't have any live streams at all because I'll be just talking to my students. So that's it for today. And thanks for watching. And I will see you next time. Bye-bye.